Okay, so we're going to start aromatic substitution reactions today. So not all of, but most of the reactions we've just talked about have had to do with the position right next to the benzene ring, but now we're going to talk about the actual benzene ring itself. So you may recall from Chem 1 that if you take benzene and add bromine to it, we would sort of expect maybe an addition reaction or something like that to occur, but that doesn't happen in this case. But if you add a small amount of iron filings or iron powder to this reaction, you get kind of an unusual product, which is that. So, okay, wait a minute. This is not an addition reaction like we're used to when you treat something with bromine, but this is a substitution. So if we do go back and look at that reaction from organic 1, we take an alkene, we add diatomic halogen of some kind, bromine or chlorine or iodine or whatever, and we definitely don't get substitution. We get addition. So certainly a clear difference here in these reactions. Another thing to note about this addition is in this reaction, the alkene, the double bond, is nucleophile, and we have a partial positive, partial negative charge on bromine atoms. Just they kind of go back and forth. But whichever bromine happens to have it at the particular time is going to be the electrophile. So these roles are the same for this substitution reaction on benzene, but without any other reagents, with just benzene and bromine. The bromine is not electrophilic enough to break the aromaticity of the ring. So if we were to try and do like an addition reaction like this, and this was aromatic, well, clearly we're going to break the double bond in order to have some sort of reaction happen, and breaking aromaticity is really unfavorable, so we don't want to do that. Now, the role of the iron catalyst is it increases the electrophilicity of that bromine. So what actually happens in the flask is first the iron and the bromine actually react with each other and make iron 3 bromide. And then we end up forming a complex between that iron bromide and another molecule of bromine, which has sort of a weird and interesting structure. It's that. So we've got the iron bromide, the FeBr3 sort of right here, and then we've essentially just attached a Br2 molecule to it. The iron ends up with a negative charge, the bromine with a positive charge. And this is the actual sort of active species that does the bromination. So, how exactly does this work? Okay, so we start with our benzene, and here I'm actually going to draw out one of the hydrogens. If we look in the actual reaction, well, that hydrogen is going to get replaced by the bromine. So clearly that hydrogen is going to go somewhere. So it's important. And then I'm going to abbreviate our iron bromide thingy to this, Br, FeBr3. Okay. So this iron bromide thing has basically supercharged our bromine reagent. And it's to the point that we can actually use benzene as a nucleophile. So we're going to break aromaticity here, which normally is a really bad thing. There's a couple reasons why it's not too horrible in this case, and we'll draw some resonance structures, but also this is an extremely strong electrophile. So we're going to form a bond between this carbon and the bromine, and then this bromine-bromine bond is going to break. Sorry, I should have done that in color, but there we go. Okay, so the result of that reaction is those two bonds stay the same. We've got a hydrogen there, and now we've made a bond from this carbon to a bromine. And then this carbon down here is going to have a positive charge. And we've also made that anion from the iron bromide. So we've got this intermediate, and we can draw some resonance structures of this. I'm going to do the first one by moving that bond over there. I'm going to move this bond down there. And those are the three resonance structures that we can draw for that cation. So, altogether, this sort of intermediate structure is called a sigma complex, or if you like, an arenium ion, because it's positively charged. Okay, and the fact that we've got these resonance structures means that we have some stabilization going on, and that's what allows us to break the aromaticity. Yeah?
What is that symbol outside the bracket?
This just means it's a transition state. It's really an intermediate, but I'll call it a transition state. Okay, so the last and final step is we're going to regenerate aromaticity, and this is actually an E1 reaction that we're going to do. But this can occur from either of the two resonance structures on the end. I'm going to draw it from this one, but it doesn't really matter. So E1 reaction. We're going to use our iron bromide thing. And I told you that the iron was catalytic, right? And so we're actually going to regenerate 3 iron 3 bromide by forming a bond between the hydrogen and the bromine. And then our bond to the hydrogen is going to satisfy that positive charge and regenerate the pi bond, and so that's going to regenerate the aromaticity. So we get that plus HBr plus iron 3 bromide. Yes.
So we're using that negative charge on the FP because the bond is breaking and helping to form that HBr.
Yes. Yeah. Okay, so I've really just talked about one type of reaction, which is bromination. But fortunately, the mechanism here is the same for a wide variety of other reactions that we're going to talk about. So, how many? 1, 2, 3, 4. There's 4 other kinds of reactions, and they all follow this same mechanism. So, first we generate some sort of really strong electrophile. Then we add the electrophile and break aromaticity. Then we eliminate a hydrogen atom to regenerate aromaticity. And so overall, this reaction is electrophilic aromatic substitution. Okay, questions on that general mechanism? We're going to see it again a few times, so we're not just leaving it here or anything, but okay. Okay, so that reaction also works with chlorine, but not for fluorine or iodine. So you can also do chlorination. And usually the catalyst that we use instead of iron is aluminum. Aluminum trichloride. And we just get substitution chlorine with byproduct HCl. Okay, so we can do bromine, we can do chlorine. We can also do a sulfonation reaction. And for this, we take benzene, and what we're going to generate is SO3H as a substituent, which is the same as saying this. It's kind of like having sulfuric acid attached to your organic molecule. And surprise, the reagent that we use to do that is fuming sulfuric acid, which is actually SO3, sulfur trioxide, dissolved in concentrated sulfuric acid, which is an awful mixture, but sometimes you have to do this reaction. This one is actually reversible, and so if you want to go the other direction, you just use dilute sulfuric acid. Water, of course, would work too, but just diluting that with a little bit of water will cause that reaction to go back the other direction. Maybe more important than sulfonation is nitration. And in the same way that we use sulfuric acid to put a sulfate group on our molecule, to get a nitro group, we're going to use nitric acid, usually dissolved in sulfuric acid at low temperature so it doesn't run away and blow up on you. And we install an NO2 group. my God, I wrote nucleophilic on my notes. Jeez. The active electrophile is this, the nitronium ion. I said this was more useful than sulfonation, and the reason for that, well, first of all, it's not reversible. So even when it comes into contact with water or anything like that, this nitrobenzene isn't going to decompose or anything. But we can also reduce this compound to an amine. So if we add zinc and hydrochloric acid, and then treat it with sodium hydroxide, reduce the nitro group, in H2, and now we have aniline. And it's a very useful reagent because we can attach all sorts of stuff to the nitrogen atom. When we have the NO2 group, that's a little bit less, well, you can't really do much with an NO2 group except reduce it to an amine. Okay, so all of the cases that we've seen so far, we have substituted a heteroatom, something other than carbon, onto the benzene ring. Fortunately, and it's fortunate because a lot of organic chemistry is trying to make carbon-carbon bonds, we can make carbon-carbon bonds with this substitution chemistry. Ugh. Come on. There we go. Okay, there's two reactions that are basically the same, just slightly different type of carbon-containing group. But the main one is the Friedel-Crafts alkylation. I assume some German dudes, I'm not sure. So, in the Friedel-Crafts alkylation, it's really kind of similar to the, well, these reactions are all similar, but it's most similar to the halogenation reactions, where we take our aromatic compound and we're going to react it with an alkyl halide of some sort. We use a chloride in this particular case. And we're going to use the corresponding metal salt catalyst, AlCl3, in the case of chlorine. And we're going to form a bond. Instead of to the chlorine, we're going to make a carbon-carbon bond between the aromatic ring and a carbon on the alkyl chain. So, as with halogenation, the electrophilicity of our alkyl halide is increased by the metal. So this is electrophilic. You know, it'll do an SN2 reaction. It'll be an electrophile in an SN2 reaction. But by itself, it's not strong enough to do a substitution reaction on an aromatic ring, kind of in the same way that bromine is not strong enough. And so we're going to create a similar complex like we did with the iron bromide, but we're just going to do it with this reagent. So I'm going to draw it sideways here. So there's our alkyl halide. When it contacts the metal salt, we end up with this, again, sort of bizarre looking complex. Bizarre because it's very reactive, and in fact what we're going to do is break this carbon-chlorine bond. Sorry, can use color. We're going to break the carbon-chlorine bond, and that's going to give us a free carbocation. Very electrophilic, and fortunately electrophilic enough to do this reaction. And that aluminum salt thing. This step in particular is kind of slow. As you might imagine, we're breaking a carbon-chlorine bond and making these two ions. But it does occur, and it occurs fast enough so that you can actually do this reaction in the laboratory. Now, there is one thing that I'll warn you about, and we'll do an example in a minute, but what do carbocations like to do before they react with other things? They like to rearrange, if they can, to make a more stable carbocation. Fortunately, in this particular case, you can't do anything to make that more stable, but if you generate a carbocation that can rearrange, it will always rearrange. Okay, so we're gonna do a good example of that in a moment. And so now the mechanism is just the same that we saw for the bromine. I mean, not exactly the same, but with some practice, you'll see that it's really the same thing. So we've got a carbocation. We're going to form a bond between this carbon and the positively charged one. So we make that intermediate. And then our friend metal catalyst is going to come back, grab that hydrogen, and then the bond moves down, reforms aromaticity. And then we get that plus HCl and aluminum trichloride. I didn't draw the resonance structures here, partially because I'm lazy, but also because that resonance structure, right, there's multiple resonance structures of this intermediate. Fortunately, the one that I've drawn is perfectly adequate to show the mechanism. And so you don't really need to draw any resonance structures in a case like this. Yes?
So is it specifically that alkane that the butane with the chlorine on that position, or can it be like a variety of alkanes?
Oh, it will be a ton of different ones. Yeah, so you can use really any alkane that doesn't have, other reactive groups on it. Mostly we'll just see hydrocarbons with a halogen attached. So we're going to do one with bromine, and we're going to do one that's going to rearrange too, so that's fun. Okay, so if we do this with FeBr3, oh, I know what's going to happen. We're going to take that propyl group and just put it right on the benzene, right? Well, that would be too easy. Okay. So we're going to first make our electrophile. So this. Okay, so we've got our negative charge there and our positive charge there. And then we're going to break the carbon halogen bond. So this bond is going to break. So we're going to end up with that plus the rest of our metal catalyst. Okay, do you see the problem? Uh-oh. Primary carbocation. It's going to rearrange. So we've got that, and we know we have a hydrogen that's there. So instead we just shift the hydrogen so that it's on that carbon. So now that carbon is happy, and we now have a secondary carbocation, which is much happier. All right, so now we do our electrophilic addition. So this is old news by now. And I think you could see what product we're going to form. It's not going to be N-propyl, it's going to be isopropyl. Form bond to that. Oh God. No. No, we're going to form, there we go, that bond. That's much better. Hydrogen there. There's our isopropyl group now that's rearranged. And then we have our metal catalyst come back to remove the hydrogen and regenerate aromaticity. The main thing I would recommend that you review here is carbocation rearrangements. So, of course, we're always trying to get to the most substituted carbocation that we possibly can. And so just go back and make sure you can see the hydrogen moving from one carbon to another in order to generate the carbocation. Another thing you might want to do is draw out explicitly the hydrogens on all of the carbons that are going to end up with positive charges, and that'll help you not forget where you have atoms and where you have an empty valence. Okay, so that's the Friedel-Crafts alkylation. The related reaction is the Friedel-Crafts acylation. So just as a reminder, if we've got just some sort of regular carbon chain coming off, that's an alkyl group. An acyl group is where we've got a carbonyl, so it's a ketone. So there's some extra advantages here. Obviously that oxygen is a helpful functionality for doing other chemistry, but sometimes you just want to add an acyl group because you can. And fortunately, we can do this in almost exactly the same way. Not going to draw the mechanism, but if you take an acid chloride or an acyl chloride, hence the name acyl, that's where chloride, that's where that comes from. And you use one of our trusty metal catalysts. You could use an acid bromide, but those are super reactive and hard to deal with, so you can buy the acyl chlorides off the shelf too. And we just get acylation like so. The electrophile that actually does the work here, in the same way that we had a carbocation for the alkylation, it's essentially a type of carbocation. An acylium ion. Okay, you're going to get a sneak peek of the homework, which I have not posted yet, but I figure it's not a bad idea to do some practice. Give those a shot. pick a single bond is right between the ring. So they're not fused. Yeah. Yeah. The attachment goes there. Yeah. Good luck on your meeting. Thank you.
Sometimes. So.
I like what I see mostly. Okay, well, okay, so you're gonna replace this bond, that CH bond, with a bond to the alpha. So you're going to use again. And then on the first one, you've done it 10.
Yeah, I had to switch it.
And now you have to scratch out.
Yes.
Is there's going to be a cross.
Okay, that's what I was just, yeah, I did.
Yes. Got 1 2 minutes. That's it. There you go. Just kidding. Yeah, yeah. That's just what to do. Okay, perfect. Yeah. Yes.
No, that's, oh, I see. We don't,
Yeah, so
just skip.
I don't know. But this,
that's the complex. Now you're going to break that carbon 41 bond. That makes right. Yeah, so then you get rid of the metal, and then you have a carbon binary carbon cation, which is going to rearrange. Yeah, but yeah, the product is a double bond.
That'd be intermediates. So, he's forgetting that the bond is formed after you take off the hydrogen.
Right, yeah, so if you have a positive charge there, that would be your hydrogen there, yeah. And then a positive charge there, and then that's your intermediate, which then eliminates to make the bond.
this has to come back.
Right, just to grab the hydrogen, or you could just show it floating away in space.
Okay, so I'm only going to.
That's okay. It's literally the first day. Oh, we're done. We're out of time. Okay, we'll talk about the answers later.
Keep guessing all.